Hello, this is Brian Kim. I'm at grade 8 and I'm attending BIS Canada. And for my science fair project, I've been working on two separate parts of programs that relate to the topic of neural networks. Um, but in this video, I'm going to talk about one of these programs, which is called a backpropagation algorithm. There is no PPT right now because I am recording about the trials and errors of my experiments. So, the details about how a backpropagation works is not yet included right now in this part of the video. But however, there are one of the key tips that I have figured out while trying to make my backpropagation algorithm to a success. So I may think that others who are working on the backpropagation algorithm, one of the key beginners, maybe that'll be a pretty useful Kickstarter in this video too. So let's get to the results first. So my complete algorithm states that it gives me this a bit of formation where it is the standardized backpropagation graph. But however, it's a lot different right here because I am guessing that these bunker points right here, there are the local minima. But however, the stochastic gradient descent, or maybe the AdGrad algorithm, they simply put my program out of the local minima bunker to eventually leading to the global minima, which is the global minima should be close to 0. Same thing right here. It's got right there, and then it gives to the local minima, and then it just nicely goes into the curve of the global minima. And this here too, it's got a little bit jaggy here, but it just plummeted down. Just cycling there, just a little bit up, and then it goes down. So, whichever case, the algorithm, while in training process, it eventually goes to the global minima. But however, here's one tip. The first tip is that a random weight sequence can be with the issue if there is a failure in training. So as I was running my program, the program that I created, the weight sequence, since it is so random, and whenever I run the same input sequences, there is a time that training completes immediately, or there is a time that training never completes itself because it might get stuck in the local minima or something like that. Um, a solution that I may propose myself, but not writing the program, is to randomize the weights every 1,000 epochs. So if you record every 1,000 epochs and then the error value doesn't seem to decrease over a threshold value of 0.2 or 0.1, then you might have to randomize the weights to start all over again in order to smoothen up the training sequence. So that's one tip. So these are the graphs that I've done with a training set. And here comes the validation processing and a whole lot of thing about overfitting. So what I've figured out while I was trying to do with the backpropagation algorithm was that many people considered about overfitting, and that overfitting is clearly important or it matters. But as I was a starter, I don't know. I didn't turn out to believe it because overfitting, it doesn't matter, right? Yeah, that happened to me 3 months ago, and then right now, I don't know. It's somehow changed my perspective because while working with backpropagation, overfitting is very, very, very important. So, to be in very simple terms, or it is somehow right, is that overfitting occurs when your computer just memorizes the whole input sequence rather than trying to analyze a pattern. So while not trying to analyze what's going on here, it just tries to memorize. If it's 2, it goes 4. If it's 3, equals 6. If it's 8, equals 16. So on and so forth. So the computer's memorizing and overfitting, not analyzing the pattern. In order to prevent this, there are many techniques. One is called overfitting. One is no, I'm sorry, I'm sorry. One is called a dropout method. There's an early stop method, and yeah, that's one of the examples that I know. Um, and both of them, I think both of them include a thing called a validation function. Um, so here's a key part about a validation function. I'm just going to open it up as an open source. So here's a validation function. Um, as you can see that I've annotated set weights. I've annotated the train nodes. Um, Same thing right here. So the train node, as seen by the function value, it just basically um, optimizes the weights, right? It changes the weights. But in a validation function, it does not change the weights. It just preserves the weight values in this specific function, in the specific neural network, and then it just simply validates whether if it is close to getting right or whether if it's far from getting right. So these are the examples in the validation sequence. It is clearly different. It is clearly different from the input sequence numbers. And although the validation sequence, it has to have more numbers into it, but I'm just sticking right here. The input validation sequence, it propagates all of these values, okay, and then it computates a net error. Same thing as a training sequence. But the difference is it does not optimize the weight values. So while using the computate net error or the validation net error, we figure out whether if the computer is overfitting or whether the computer is doing its progress. That one example case happens where the early stop method is when if the validation net error decreases and then it suddenly tries to increase, then that means that the computer is overfitting. So it stops immediately and then it just goes to the testing phase. So that's an early stop method. But what I have done was a comparison method where you just keep on training until the validation net error is smaller than or equal to, let's say, 0.1. That's what I've done right here. Then you go to the testing phase. Now, there are clearly advantages and disadvantages. Say, what if the validation net error does not decrease? Well, it's just going to go on forever. But another solution to figure out is, well, randomize the weights, and then let's do it all over again. Well, that's another simple case. Um, so let's try and write it down. And in the test input sequence, here are the numbers that basically follow the pattern. So let me just explain the pattern to basically think how the computer is doing. So I made a pattern right here. The pattern is that the first number, right, it's arbitrary. It can go up to the first digit to any other kind of digit. So there's a first digit number, which is 2, an integer. And then the second number depends on whether if the first number is multiplied by 2. So it just goes like this. So it's 2, 4, right? If it's 3 multiplied by 2, it's 6, right? 8, 2, 6, right? And it goes on, and then these valid patterns, they represent as 1, okay? So 1 means that the pattern is correct, and 45, 56, well, 45 times 2 is 90. No, it does not. So that's 0 right here. So the pattern goes on. I have of all these bunch of numbers. Same thing as a validation sequence. It follows a pattern, somewhat, right? These two patterns, they do not follow it, and also the testing sequence right here. It does follow the pattern. One of these guys, these don't follow the pattern, and this follows the pattern. As I told you, I didn't put the randomized weight sequence yet. It's gonna take a while for me to program, but this is for just for a overview of what I'm doing. So as I'm running this down, as you can see, you got the validation error and the training error. The training error is simply very high compared to the validation error, which in this case, the weight matrices are completely randomized in a how should I say it? In a bad manner, right? So it's completely wrong, I could say. But let's wait for a minute. I think it's stuck on the local minima. Yeah, it's stuck. So, let's say that the program basically randomized the weights again, and then let's run it again. And here we go. It suddenly bumps down to 1, and there we go. Okay, so randomizing weights does help. So let's take a look at the testing sequence. So there must be a text value. Satisfactory. That means that the net error is smaller than or equal to 0.1, which in this case is right. So its contents of input, 88,176. It does go right. 1128. It does go right. It does go right. It does not, which is simply goes to 0 is close to 1. Right? This is, right now, this example itself, it is useful when the computer wants to check test answers, right, by students, right? If the math is right, corresponding to this pattern, well, you just get the computer to analyze the number of set inputs, and then you just check the answers of all students, right? Let's see. Yep, that doesn't work. Yes, and we go to testing phase where we have 55 and 110 and 4488. Let's go backwards, shall we? 4488, of course. 9999, yep. 9988, it's wrong, yep. And 55 100, it's right, yep. So right now, it's going very, very nice. Okay, but let's play around with the numbers a little bit. Let's just make this wrong, right? Let's say 55. I think it's 100, a student says, and then 99. I think it's 198. I think it's correct. And 99, 99, and 44, 88. Let's add another number. 65 to, I think it's 135. Okay, so let's try and train this guy. See if it works. 65, 135, yes, it's correct. 4488, yes. 99, nope. 99, 198, yes. 55, 100, yes, it's not correct, so it's close to 0 rather than 1, right? Yeah, so it does try and figure out the pattern. I don't have time to play around a little bit more. So, yeah, that is the whole process of backpropagation. So this is all based on the proof that, yes, my program works, and yes, I've done it in 3 months, and yes, this is my science fair project. So, but here are a couple of tips, okay, for somehow the people who are trying to construct a neural network. So what I've used was I used a stochastic gradient descent algorithm while trying to optimize the weight values, stochastic gradient descent, because batch gradient descent, it takes a longer time to computate the values, it takes more memory, and the batch gradient descent easily gets stuck at the local minima. However, the stochastic gradient descent solves almost everything that the problems that I stated. And inside the stochastic gradient descent, I've used a ADGRAD algorithm that gives a, how should I call this? Um, gives an adaptive learning rate. Um, because if there is no adaptive learning rate, let me just give you a nice overview. Okay. Let's give it as a Desmos graphing calculator. And I'm going to just simply input a quadratic function, okay? Okay. So this is a quadratic function, okay? Let's say it goes as a limit to net error of 3, okay? So the computer wants to limit to go to here, right? The global minima, 0, 0. Let's say there's a ball right here. There's a ball right here. And if you calculate the derivative, simple math, no, not simple, but math that relates to backpropagation, I hope you learned it. If you calculate the derivative and then you multiply with the learning rates, then the learning rates is basically how fast the ball is going to go per epoch. So if the learning rate is 0.7, it's going to go like this fast, right? Whoosh to whoosh. Um, and then it goes on 0.7 whoosh whoosh. You see the point? It does not go 0, 0, it just goes pretty far right here. Okay? And then it tries to go to 0.0. Calculate the derivative, multiply 0.7. Whoosh whoosh. Right? As you can see, it does not go to the global minimum. It goes to a very different kind of perspective, and a whoosh and a whoosh. And then it's just gonna grow like a crazy Viking ride, right? It's just going to go very, very high in detail. No, not high, very, very high in perspective wise. So here are the things that I have made mistakes while going with that learning rate. So if I go to my drive, there must be a graph. Science fair. Okay. So this is the error. So it does decrease, right? That's what learning rate does. And then it somehow increases again, okay? That's one case. It just drops down. It somehow goes to this local global minima and then it just increases so fast. Um, but this is the perfect case where it just basically completes its training. But this is a time when it's very, very lucky. This happens when the quadratic graph itself is very, very large. It's very, very large, and then that a certain amount of a learning rate is just adequate for that big curve. Okay? But in most cases, the quadratic graph is very, very small in width and length, so that's why it just goes out of the grid. That's one of my failures. So always use a adaptive learning rate, which is AdGrad. I'm going to show you the AdGrad algorithm itself. The pseudocode is somewhere around the internet. Just Google AdGrad, and then there is a guy, I don't know his name, but I'm sorry, but there's a guy who knows very, very well about these kind of stuff. So I thank you to that guy who introduced the AdGrad algorithm to me. And always, I use Quora in order to ask a bunch of questions. So Quora is a really, really nice website. So if you want to just ask some questions, use Quora. There are a bunch of professionals who can just happily answer your answers. So here is the AdGrad algorithm. So yes, it does use a batch gradient algorithm. So it just gets a mini batch. It's a mini batch style. So it's something like this. So here's a whole source. Try and encode whatever you like. But the easiest type is a pseudocode. So just Google AdGrad, and then it's just going to give you a very nice adaptive learning rate. So here's the whole weight optimization, and here's a node. And each node I have I have made the equation as a hyperbolic tangent. because if you see certain types of graphs, the hyperbolic tangent is a lot better than the sigmoid function, in my experience. Okay, um, there is no clear representation or proof that the hyperbolic tangent is better than the sigmoid, the logistic sigmoid function, but by experience, the program seems to do well or much better at the hyperbolic tangent than the sigmoid function. So that's one tip to do it, okay? So just calculate the derivative of the hyperbolic tangent, and then you're set to go. And the most important thing, validation errors, validation sets, and overfitting, right? Try and solve that. One of the tips that I've given to you. And also, while making a backpropagation algorithm, always try to make your hidden nodes layer and nodes so that you can customize them. So what I did was that I can make an infinite amount of layers and infinite amount of nodes inside my program. This enabled me to experiment with a lot of more variation. Okay, so right in here, this pattern sequence cannot work if there is at least a minimum of 6 layers. Um, because I don't know, because there is more brain complexity. It's common sense, right? If you have more neurons and more complexity in your brain, you can solve more complex problems, more complex patterns, right? So that's why Einstein's brain is bigger than anyone else. Sorry, stereotype. Yeah, so always try and make your hidden nodes in your program so that you can add infinite amount of layers and infinite amount of nodes. That will give you a lot more stuff. And also for the input nodes, I could put 100 input nodes or 2 input nodes. It doesn't matter for me. And output nodes too. I can make 100 output nodes or just 1 output node. So make these guys very, very adaptable. Okay? So that's so far it. So that's my tip for the backpropagation. What I've learned, what's very surprising, is that the program actually learns itself. The program actually learns any type of pattern unless there is a pattern in these numbers. So thank you for listening. This was Brian Kim in grade 8. And yeah, if you're more interested, you can check out my channel more. In the next video, I'm going to take a look at the gradient genetic algorithms that I've created. Thank you.